In some sense, the most general group you get as follows. If you start with any set, call it the set T. And you let G be the set of all bijections G from T to itself. So that means one-to-one and onto maps from a set to itself. All bijections. Then that's a group that sometimes I'll denote it by the symmetries of T, or the symmetric group of the set T. So this is a group under composition. Composition of bijections. If you compose one bijection with another, you get a third, because if two maps are one-to-one and you compose them, you get a third one-to-one map. If two maps are onto and you compose it, you get another onto map. So that's the composition law of transformations. The identity element is the identity transformation that takes every element in the set T to itself. That's certainly one-to-one and onto. The inverse element is the inverse transformation. If you have a transformation that's one-to-one and onto, you can send the transformation back. That's G inverse. And composition of maps is associative, just like we proved composition of linear maps is associative. Because if you have three maps and you compose them, no matter which way you do it, then it's the final map that takes an element in T first to this map, then to that map, then to the third thing in T. So this is the most general group in some sense of the word. One second, I just want to finish. And all groups we'll see somehow arise by putting extra conditions on this invertible bijection. So for example, this group GLNR, how did that come about? Well, I started out with a set which was Rn. The set which was Rn. And I considered all invertible maps from Rn to Rn which preserve the linearity, which preserve the structure of a vector space. That's not all maps, but the ones that preserve some structure. And that's how I got invertible matrices. So we're going to see that this is somehow, and this was Galois's big idea, that when you studied maps or symmetries of a set, that was one group, and then you could get very interesting groups by studying symmetries that preserve some extra structure in the set, like some linear structure on the set. And in particular, we're going to have one very famous group where this T is the set of a finite set, and all finite sets are determined by the number of elements in them. So the set from 1 to n. Then we'll call the symmetry group of T the symmetric group S sub n. We'll just write it that way. And this turns out to be a group with only finitely many elements in it, because there are only finitely many ways you can permute n different objects. How many ways are there of permuting n different objects? Yeah, so this is a group where it's a finite group of order n factorial, and you'll find that it's non-abelian, and you should check that once n is at least 3. So there's a finite group with 6 elements in it that's non-abelian. The permutations, the one-to-one maps of a set of 3 things to itself. And you should play with that a little bit.